once we get into liquids and gases, we start to have to worry about things like rotation and vibration of individual molecules. You have to always worry about vibration of the bulk solid. That's kind of a translational energy thing. But suffice to say, also we discussed electronic excitations. We said that electronic excitations were much larger in energy, and so you need a large amount of energy in the environment in order to populate electronic states. Take-home message is that depending on what temperature your system is, it will hold more or less energy. As you increase the temperature of the system, if new energy storage modes become available, your system will take on that energy. And so the total internal energy content of a system depends on its temperature. Your energy storage depends on your temperature. It's pretty easy to see that since enthalpy and energy, or since internal energy is a part of enthalpy, it's the first term in that enthalpy term, that the enthalpy also is going to be dependent on temperature. The result of this is that no chemical reaction will have the same delta H value at one temperature as it will at another. The delta H of the reaction is always H of the products minus H of the reactants. But if your products and reactants both change their H by some amount at a new temperature, then delta H is also going to change, right? So because at different temperatures your molecules are storing different amounts of energy, the delta H of the reaction at one temperature will be different than the delta H of the reaction at a different temperature. And that's all I'm saying here is that delta H at T1 does not equal delta H at T2. The tool that we use to know how delta H's are going to vary, or delta H's of reactions or enthalpies of individual species are going to vary with temperature, is this thing called CP, the constant pressure heat capacity. So CP is the derivative of the Q associated with the constant pressure process over the differential of T. So it's dQ over dt. We know that dQ or the integral of dQ for a constant pressure process is delta H, integral of dt is delta T, and so this can be expressed as delta H over delta T, dH over dt. And if you take this dt and you stick it right there in front of the CP, you get an equation that says that dH is equal to CP dt. I didn't write that on there, but you can put it in your notes. dH is equal to CP dt. The integral of dH is the integral of CP dt. So integral of dH is delta H, so it's H of T2 minus H of T1 is going to be equal to the integral of CP dt. Therefore, the enthalpy of a species at some temperature T2 is equal to the enthalpy of that species at T1 plus that integral of CP dt. And the heat capacity, CP, again, all that describes is the actual dependence of energy storage on temperature. It itemizes how much energy is going to be dumped into a system with a particular change in the temperature. So, with that said, let's say that we have a reaction, and I'm not going to put in all the stoichiometric coefficients. I'm just going to make up a mock reaction, a hypothetical reaction without stoichiometric coefficients. But when you do this at home or on an exam, you'll have to remember your coefficients. Let's say we have a reaction that goes from reactants to products. Delta H of the reaction is going to be equal to H naught of the reactants. We'll call this T1. H naught of the reactants, or products, sorry, minus H naught of the reactants. Well, H naught of the products at T2, so this is at T1. At T2, H of the products is going to be equal to, we'll call it H naught of products at T2, is equal to H naught of the products at T1 plus that integral of Cp dt from T1 up to T2. And similarly, H naught of the reactants at T2 is equal to H naught of the reactants at T1 plus the integral of C sub P of the reactants. I should have written products up here. dt. And therefore, delta H for this reaction is going to be H of the products at T2 minus H of the reactants at T2, which is equal to H naught of the products at T1 plus the integral of C sub P of the products dt. We're subtracting from that H naught of the reactants at T1 plus the integral of C sub P of the reactants dt. Start to condense this. So look for delta H of the T2. And we get that delta H at T2 is equal to, I'm going to group this H naught of the products minus H naught of the reactants. Group those two together. This minus this plus C sub P of the products minus the integral of C sub P of the reactants dt. And I should have a dt in there too. This term right here is just delta H naught of T1. This term depends on the relative heat capacities of your reactants and products. So in general, C sub P of the products and C sub P of the reactants are not going to be the same. And so you'll have so this term, depending on which one is larger, you'll have a positive or a negative term right here that adds or subtracts from H naught of T1. So all that's saying is that at T2, the delta H of the reaction is either going to be higher or lower than it was at T1. And whether or not it's higher or lower will depend on the relative magnitudes of C sub P of the products and C sub P of the reactants. For many species, the heat capacities change with temperature, and so there'll be some specific temperature dependence on the heat capacity. As the temperature changes, the heat capacity will increase or decrease or whatever. We saw examples of that. Most real situations are like that. But if you keep your temperature range narrow, you can restrict your reaction to places where the heat capacity is relatively constant. And if, to the extent that that approximation is true, your heat capacities can come out of the integral, and you have this term C sub p of the products times the integral of dt minus C sub p of the reactants times the integral of dt, and again this is T1 to T2. These constants can be grouped together. You get C sub p of the products minus C sub p of the reactants times the integral of dt, which just ends up being delta t. And so that is just kind of the mathematical way of looking at, of tracing temperature-dependent changes in reaction enthalpies, right? So because products and reactants don't have the same C sub p's, there will be some difference in the delta H at some temperature other than the standard temperature for which you calculate the values. All right, so let's take a look at something here. Number 7, just want to go over the homework with you a little bit so you know what we're asking. Number 7, you're told that the molar heat capacity of a substance is C sub p equals A plus B times T minus C times T squared. Which situation is that? Is that the situation where C sub p is a constant and it can come outside of the integral? Or is that a situation where C sub p is not a constant and must be included in the integral? That C sub p is a function of temperature, right? So this is the case where C sub p is not constant. We're not restricting our temperature range to small values, and so we have to have the full temperature-dependent form of the heat capacity included. And you're told that you got a heat capacity of a substance. It's A plus B times T plus C over T squared, and they give you the A's, B's, and the C's for all of these different substances: carbon dioxide, graphite, water, nitrogen. And they're just saying take carbon dioxide and figure out what the change in its enthalpy is when it's heated from 15 degrees Celsius to 87 degrees Celsius. So here you're just going to go back to that equation, just not delta H. Now we're just considering H. So H of CO2 at T2 is equal to H of CO2 at T1 plus the integral of C sub P dt from T1 to T2. You can move that H of CO2 over here, and that becomes H of T2 minus H of T1 is equal to the integral of C sub P dt. And that's just the delta H they're looking for. So this delta H for carbon dioxide, we're not talking about delta H of a reaction. We're talking about the change in the enthalpy of the carbon dioxide when it moves from one temperature to another, right? And that's all you got to do. You're going to have to execute those integrals. Integral of a constant is just that thing times the function. So for that A term, the integral of A is going to be A times T. For that B times T term, integral of X is 1/2 X squared, right? So you'll get that in there. And then the other one, you got the integral of T to the negative 2. And so that's going to be negative T to the negative 1 is going to be the integral of that. You guys can go back and double check your calculus books, but not horrible calculus there. It's not the worst stuff in the world. So that question is just a, just a question of doing that. Six, they're just talking about different changes that matter can go through, so solid to liquid to gas, etc. And they're asking you to talk about the signs of the heat, the work, the change in the internal energy, and the change in the enthalpy. And so you're just going to look at those and ask yourselves how those functions are changing. That shouldn't be too bad. It's not going to be too easy either. Number 4 is just an ideal gas problem. We're going to do a couple more of those. We're going to do a couple more of those on Thursday to freshen you up. I want to find an enthalpy problem here. You know what? Instead of showing you another problem, let's do some group work. Let's have everybody work on number 7 together, and I'll introduce a new problem to you on Thursday. So I really want to make the most of doing this. I want you guys to teach each other, so I'm going to try to organize some structure. I want you to turn your tables into circles, make groups, get together, start working on this problem, communicate.